Apart from the Moon, the brightest object in our sky at the moment is the planet Venus. Known historically both as the morning star and the evening star, Venus played an important role in the history of our understanding of the universe, and it's particularly fitting that we think about it now in this year of astronomy, given that Galileo's observations of the planet were so important. Before we tell that story though, let's just think about planets in general to start with. Of course we can easily see without telescopes the planets Venus, Mars, Jupiter and Saturn, and we know there are others too, such as Mercury, Uranus and Neptune. Everyone today is also aware that the planets orbit the Sun. That idea, however, was hotly debated in the history of astronomy. The reason why the planets cause so much consternation is that their behaviour in the night sky is so different to that of the stars. The stars all stay in relatively fixed positions in the sky, with the constellations, for example, not changing significantly from year to year. The planets, however, seem to wander from night to night, separately from the stars. Indeed, that's what the word planet actually means in Greek, wanderer. The simple idea that they went around in perfect circles lying in a series of spheres around the Earth just couldn't explain this easily. Even in the pre-telescope age, astronomers were very good at marking out the positions of the planets and the stars, and when they traced out the tracks of the planets in the night sky, they were baffled by times in which they seemed to stop moving, drift backwards, and then continue in the original direction. Look at this example of a photograph taken of the track of the planet Mars as it varies from night to night. Adding the images from different nights on top of each other, you can see that not only does the planet move compared to the stars, but it also turns these funny backward loops. Explaining this motion was one of the central puzzles of early astronomy. Given the religious or philosophical beliefs that the Earth was at the centre of things, and that the objects in the sky rotate around us, then quite complex proposals had to be developed to explain the behaviour of the planets. Simply having them go around the Earth in circular orbits couldn't explain this wandering motion. A model which did very well at explaining some of the observations was that developed by astronomers such as Ptolemy, in which the planets didn't just circle the Earth, but actually moved in circles around a centre which itself orbited the Earth. This type of motion is called epicyclic, and you can see what I mean in this diagram. Looks complicated, doesn't it? But this is the type of imaginative scheme that had to be dreamt up in order to explain the observations, until people had the nerve to think differently about the centrality of the Earth and mankind in the universe. To fit the increasingly accurate observations, however, the model had to be modified by adding extra epicycles, as some people suggested, or as Ptolemy proposed, shifting the centre of the orbits a little away. More and more, the circular, Earth-centric model started to look untenable. Of course, the next key stage was the recognition by Kepler that not only were the planets going around the Sun, but that the orbits were elliptical rather than circular. But that's another story. So what did Galileo do? Well, he turned his new telescope to the skies and noticed that Venus exhibited phases, much in the same way as the Moon does. The Moon does indeed go around the Earth, and its position relative to the Sun determines the amount of its face that we see illuminated as it completes its orbit. However, in the case of Venus, it never strays far from the Sun in the sky, and so the only way that its phases can be properly explained are by considering it as orbiting the Sun. This diagram attempts to show this. It's perhaps a subtle point, but for those arguing against the Earth-centred view of astronomy at the time, it was a critical observation, and one which caused no end of difficulty for Galileo from the Catholic Church, who sentenced him for house arrest for the rest of his life. And bizarrely, it was only in 1992 that Pope John Paul II allowed the Church to officially concede that the Earth was not stationary, and expressed some regret for how Galileo was treated. But what about the planet Venus itself? What's it like? Well, this image shows the relative sizes of the four inner planets of the solar system, with Mercury at the left, then Venus, the Earth, and Mars. Clearly, Venus and the Earth are very similar, and indeed are often referred to as sister planets. Observations of the planet show that it has a thick and murky atmosphere, and we know that it is largely composed of carbon dioxide, with some sulfuric acid rain in the upper atmosphere, and the occasional lightning outbreak. The pressure and temperatures on the surface are really dramatic, with a surface temperature of over 450 degrees Celsius. The conditions are so extreme that early probes to the planet were crushed by the atmospheric pressure before they reached the surface. Interestingly, and perhaps somewhat prophetically for us on Earth, the atmospheric conditions of Venus arose because of a catastrophic runaway greenhouse effect. The upper parts of the atmosphere also reflect away the sunlight, making it impossible to see the planet's surface. This has, however, now been mapped in great detail using radar from the Magellan Orbiter. Try and answer the following two questions. Firstly, how long does it take for Venus to complete an orbit of the Sun? In other words, how long is its year? Secondly, how long is a Venusian day? In other words, how much time does it take for Venus to rotate once on its axis?